All right, so we're starting a new chapter, and remember at the end of this chapter, which is only 3 sections long, we'll have a test on chapter 7 and 8. Now, chapter 8 is about conic sections. We won't be covering every section that's in the book, but we'll be covering the important parts for moving forward to the end of pre-calculus and into calculus, which are the primary conic sections. I'm going to let you read that little paragraph to yourself, and then when you're ready, we'll go ahead and define conic sections and talk about where they come from. So to understand conic sections, conic coming from the word cone, we need to know what a cone is. And the way that we define a cone in mathematics is not the same as like an ice cream cone or a traffic cone. When you're thinking of a cone, you usually just think of like a circle that goes to a point. However, that's actually only half of a cone in the mathematical sense. When we talk about a cone, we talk about a line and a point, and the line is rotated around the point. And so you end up with kind of a double-sided cone. To demonstrate this, I made a GeoGebra activity. And I'm going to define these and then I'll show you the activity which you can interact with on your own computer as well. The generator is the line that is rotated around the vertex, which is the point on the line which the line, the generator, is rotated about. And then the nape, let me see if I can get the camera to focus here. There you go. The nape is just one side of a cone. One side of a cone. So either above or below the vertex. And this is what we usually think of as an ice cream cone. Is one nape of a. So what I want to do is look at the GeoGebra file. So if I go over here, I hope it's still recording, and I'm going to refresh the page so that you can see in this first activity here, we start with a line, and on that line is a point, and the line is going to, and it should start automatically, rotate around that point. And as it rotates, it creates this shape which kind of looks like two cones put together, but really that's the definition of the cone. And so what we can do is we can look at that conic shape, and we can have a plane that kind of cuts through the cone. And as it cuts through the cone, it creates these different shapes that are called conic sections. And so if we look back at the notes pocket, all conic sections can be expressed as a second-degree equation in two variables. What that means is that we've got an ax squared, but we also have a bxy, that's degree 2 with two variables, cxy squared, dx, ey, and then f, a constant. Okay, so if you ever have a quadratic equation in two variables, you know that it can be expressed as a conic section. So what are our conic sections? Well, if we take a plane and we cut the cone in a way that we get just one side or one nape of the cone is intersected by our plane, it's a parabola. And we've seen parabolas before. The equation of a parabola is y equals x minus h squared plus k. And that's the primary way that we will write our equation of a parabola for now. Later on in this video, we'll talk about other ways to write the equation of a parabola. If we have the plane and it cuts across the nape so that it intersects both sides of the nape, then we end up with a circle, or if it's at a slight angle, an ellipse. So notice this is actually perpendicular to the axis of symmetry of our cone in order to get a circle. The equation that we look at for that is x minus h squared over a squared plus y minus k squared over b squared equals 1. And if a equals b, this is a circle. And we call that r. If a equals b, we call it the radius r. if we have a plane that intersects both napes of the cone, that's how we get a hyperbola. Remember hyperbola 1 over x. There's a proof of that 1 over x is a hyperbola, actually, that I posted on the topics page. And we do that equation as x minus h squared over a squared minus y minus k squared over b squared equals 1. And actually those two fractions can switch places depending on which direction the hyperbola is facing. We'll get into that later. And then we have our special cases of our conic sections, which is if the plane intersects the cone in just the perfect way that it makes a line, y equals mx plus b. So we can see that a line actually can be a conic section as well. And then if I have the plane intersecting only the vertex, then we get a point, which we write as xy. And then we have the plane intersecting multiple lines, and we would just write those with their separate equations. Y equals mx plus b and y equals mx plus b. But we would use a subscript to denote that they're two different lines. Okay, so today's main part of the lesson is going to be talking about parabolas. So we're going to be just looking at parabolas. We've already kind of looked at these three cases separately. So today is parabolas. Next class, circles and ellipses. And then the last class before the test will be the hyperbolas. We'll have a review day, and then it will be the test. Let's take a look. So up till this point, we've been using the algebra of a parabola, which is just looking at the equation and looking at if I have an x value, what y value will I get? Well, the geometry behind that is also very interesting, and that's what we're going to investigate a little bit more. So the algebra of a parabola, we have our equation. If we subtract k from both sides, we can get this new way of looking at the formula where we have y minus k and x minus h. Now notice if k is positive, my graph will move up. So again, just like when I group x and h together, h kind of acts backwards from our intuition. When I group y and k together, it does the same thing. Okay, so one way that we can think of this is that the y value that will make the 0 is the y value of the vertex. And the x value that will make the 0 is the x value of the vertex. And that means that our vertex will have the value hk. The geometric definition of a parabola is that it's the set of all points in a plane equidistant, so the same distance, from a particular line, which we call the directrix, represented here on this diagram, and a particular point, which we call the focus. So it's all the points that are the same distance away from this line and this point, which means that the vertex is exactly halfway in between them if you draw a perpendicular line from the directrix to the focus. And then every point on here, if I draw the distance from the focus and the distance to the directrix at a right angle, those two will have the same distance. So we can draw this diagram that kind of demonstrates that the distance from the focus to the vertex, if we call that 1, then the distance from the focus to the directrix is 2. And because we can draw this circle that goes centered at the focus, distance of 2 to the directrix, and that's also going to be a distance 2 then from the focus to the parabola. And so we have this distance across the parabola that gives us 4 times the distance from the focus to the vertex. So we call that distance p. Then the distance across is 4p. Okay, so p is called the focal length. Focal length is the distance from the focus to the vertex. And then we have the focal width, which goes all the way across the parabola, is 4 times p. And the focal width should be positive, so we always put that in absolute value bars when we're calculating it. So let's look at how do we find these values and what do they all mean. There's a little table for you. I'm going to go ahead and move the page off camera. Okay, now I've already filled in the table. so that I could write it a little bit more neatly than I can around the camera. But let's talk about each piece. So the standard equation, this is the function form that we've seen before where x is squared. But instead of writing a as my... All right, so I filled in this table so that I could do it with a little bit neater handwriting than I can by writing it around the camera. But let's talk about each piece. So the standard equation, and this is the one that we've seen before for functions with x that's squared, except now instead of having a leading coefficient of a, as we've seen before, we have our focal width, which is 4p. And what that means is that 4p is actually equal to 1 over a. And just like we've seen before for this function, that's an upward or downward facing parabola. If my focal width, or if my focal width is positive, it's upward facing, because if the focal width is positive, then our a value would be positive. If the focal width is negative, then that will be a downward facing parabola. If we look at squaring our y term instead, it's the same equation, but x and y have kind of switched places the way that we would for an inverse, and that makes the parabola open sideways. And so to open left, we have a negative focal width, and to open to the right, we have a positive focal width. Sorry. In the next row, we have the focus. The focus is the point that's inside of the parabola. So notice if we start at the vertex, we go a distance of p to get to the focus. So that means for an up and down facing parabola, we're changing our y value by p. So we take the vertex, hk, and we add p to the y value. The directrix is the same distance p away, but below the vertex. And so our directrix is the horizontal line y equals k minus p. Vice versa for our sideways parabolas, it's a distance of p away from the vertex sideways, so it's changing our x value, and then our equation for the directrix is a vertical line, so x equals h minus p. Our axis of symmetry here, which would go straight through the focus and the vertex perpendicular to the directrix, is going to be x equals h, and here our axis of symmetry goes directly through the focus, the vertex, perpendicular to our directrix, y equals k, where p is our focal length, and our focal width, which we always write as positive when we call it the focal width, is the absolute value of 4p. Let's take a look at an example of when we would use these. So in example 1, we have an equation and we want to find the focus, directrix, and focal width of the parabola. Well, to find these things, we need to know our values for h, k, and p. So we need to find h, k, and p. Well, from our equation, we can see that x is squared without adding anything to it. Y also has nothing added to it. So k is 0 and h is 0. That's nice. That means our vertex is at the origin. P comes from this value here, which, because it's attached to the one that's squared, is actually our a value. So we need to calculate p. Since a is 1 over 4p, we can calculate our value for p from this ratio right here. So negative 1/3 equals 1 over 4p. Cross multiply, 4p equals negative 3, so p equals negative 3/4. And then using the table above, we can find the focus is h, comma, k plus p, which is 0, comma, negative 3/4. The directrix is y equals k minus p. Y equals negative of a negative makes 3/4. And the focal width, which is the absolute value of 4p, is 4 times negative 3/4, which is 3. On the next page, we're doing it backwards. We are given information about the line and or the parabola, and we want to find its equation. So we know that the directrix is the line x equals 2, and we know that the focus is negative 2 comma 0. So if we sketch a picture, x equals 2, 1, 2, the point negative 2 comma 0, that tells us that the vertex is halfway in between, and it opens away from the directrix and around the focus. So here's a sketch of our parabola. So this tells me a couple of things. First of all, it opens sideways, so my y is going to be squared. My vertex here, halfway between negative 2 and 2, is actually at 0, 0. So I can say h is 0, k is 0, and we need p. Well, p is the distance between the focus and the vertex, and that is a distance of 2. But it's to the left, and so p is actually negative 2. Now p, we think of it as a distance, but again, within a coordinate plane, just like when we were talking about trigonometric functions, can be negative if it's going in the negative direction, which is why our focal width is always in an absolute value. Okay. Now we want the equation of the line, so the equation of the parabola in standard form. My y is squared, so I have my y minus k squared equals 4p times x minus h. Y minus 0 squared equals 4 times negative 2 times x minus 0. Y squared equals negative 8x. And that is the equation in standard form for a conic section. How we used to look at this, we used to say x equals negative 1/8 y squared. And that's still true, but this is our old way of looking algebraically. This is our new way of looking geometrically. So the next question should be, well, what if my vertex isn't 0, 0? Because we've seen two examples where the vertex was 0, 0. So let's look at example 3, where we'll look at where is my vertex if it's not 0, 0. And remember, we call the vertex the point hk. And that tells us how far it has been translated, h units to the right and k units up. So if h is negative, it's going to the left. If k is negative, it's going down. Just like an ordered pair, well, this is an ordered pair, our h and k values tell us where our parabola starts from. So in example 3, we want to find the equation of a parabola. We have a vertex and a focus. Again, I'm going to start by drawing a picture. Vertex is at 3, 4. The vertex is actually on the parabola. Focus at 5, 4 is not on the parabola, but we know the parabola goes around it. Now the distance here is 2, so then our directrix is 1, 2 units, the opposite direction. Spacing is not equal, but okay. So the equation of this, it's a vertical line, x equals, this was an x value of 3, 5, 2, 1. So we didn't need the equation of the directrix, but that helps us kind of see what's going on. So we have our p value is 2, h value is 3, k value is 4. To find the equation of the parabola, it's opening sideways, so my y is squared. Y minus k squared equals 4p times x minus h. Y minus 4 squared equals 4 times 2 times x minus 3. Y minus 4 squared equals 8 times the quantity of x minus 3. This is standard form, so you can just leave it like this. You don't have to distribute that 8 because the 8 actually is the focal width. Here. Let's look at example 4. All right, so in example 1, we saw how to find h, k, and p if we're given the equation. Example 2, if we had parts of our parabola, such as the focus and directrix, we could find the function by finding, again, h, k, and p. And then example 3, doing the same thing where h and k were not 0, 0. So in example 4, we're looking at, okay, so now how can we use our tools in order to help us understand these functions and graphs as well? And that is to use our graphing calculator. But if we have it where the y is squared, we can't put this directly into our calculator because our calculator in function mode has a y equals feature, not an x equals. So in order to graph this, we need to find the implicitly defined functions. Now remember, implicitly defined. That means we want to solve for y. So we're going to solve for y here. In order to get y by itself, I need to get it out of that square. So we can use the square root property, where I take the square root of both sides, plus or minus. Y minus 4 equals plus or minus the square root of 8 times x minus 3. Plus 4, not too bad. Y equals 4 plus or minus the square root of 8 times the quantity of x minus 3. This is two different equations, right? We have y1 equals 4 plus, and we don't really have to simplify if all we're doing is graphing, because the calculator will do the calculations for us. Oops, that one should be a minus. And so we put y1 and y2 into our calculator. Now, without a calculator, what do we know this will look like? So what are we expecting this to look like? Well, here I know that k is 4, h is 3, so 1, 2, 3, 1, 2, 3, 4. The y is squared, and my focal width is positive. So I'm expecting it to look like this. When you actually put it in your calculator, what you might end up with is a graph that looks like this. And what's happening there is it appears to be a gap between the two functions. Now, this is a very common grapher error, and we've seen this before when we were looking at implicit functions. But if that gap really bothers you and you really want it to graph there, what you have to do is center your screen at that point. If you make 3, 4 the center of your window, it should, not always, but usually, fill in the gap. And this is just an artifact of how the calculator is calculating those points. Okay, so if the gap is really big and you want to see how big it is, you can always decrease your x and y step, or your the values of how frequently your calculator is calculating the x and y values. However, knowing that this is a calculator error, if you see that gap, you can logically say, well, I know this was a parabola, so I know that that's just a calculator artifact. Okay, so again, knowing how to use your calculator is much more important than always turning to it to do the calculations. Let's look at the next page. All right, looking at example 5, we want to show that this equation is actually a parabola. Now, to do that, we want to put this equation into the standard form of a parabola. And as some of you may have guessed, in order to do that, we need to complete the square. We need to be able to write this as the perfect square. Now, last time we talked about completing the square, I said that you can use HK, use those formulas. However, now we have two variables. And so there's still a way to apply that equation, the vertex formula for H and K. However, in this situation, it's going to be easier to just complete the square. So, as a reminder, completing the square, I want to rewrite this by collecting all of my variables together. Y squared plus 2y minus 6x, and then I want to put all of the constants on the other side, equals negative 13. The one that's squared, so y squared, is the one that I want to complete the square on. So I take the middle coefficient and say 2 divided by 2, 2 over 2 is 1. Raise it to the second power, 1 squared is 1. That's what I want to add to both sides of my equation. So I have y squared plus 2y plus 1 minus 6x equals negative 12. And this gives me y plus 1 squared by factoring equals, I'm going to go ahead and add the 6x over here, 6x minus 12. And then to put the rest of this in standard form, I need to factor out the coefficient of x. So I have y plus 1 squared equals 6 times x minus 2. This is standard form, and therefore standard form of a parabola. And therefore this is a parabola. And then we need to find its vertex, which is hk. H is 2, k is negative 1. Its focus, which means we're going to need p. And I know that 4p is 6, so p is 3/2. Which way is this opening? It's opening to the right. We have 2, negative 1 opening this way, because the y is squared and the 6 is positive. So I need to add this to my x value. So the focus is 2 plus 3/2 comma negative 1, which is 7/2 comma negative 1. And then lastly, the directrix, which will be a vertical line over here. X equals 2 minus 3/2. Again, convert that and subtract equals 1/2. X equals 1/2. Sorry about that. I'll pull the camera down. So again, finding the standard form, finding h, k, and p, and then substituting those into our pieces in order to solve for the vertex, focus, and directrix. Now, why do we care so much about conic sections? Well, conic sections represent a lot of useful things, a lot of things that occur in the natural world, such as orbiting or reflecting or free falling. So parabolas are often used for free fall. We've seen that in the free fall formulas that we've been using throughout the year. But what I want to look at now is the reflective property of a parabola. And if you take a parabola and you rotate it in three-dimensional space, it creates this shape called a paraboloid. It's a three-dimensional parabola. And what's nice about that is if I were to shine light directly into a paraboloid, it would reflect back to the focus, which means that if I emit light from the focus, it will emit out, and that's how a flashlight works. So since this works both ways, we can use this to collect things and to emit things. So radios, satellites, microphones, things like that. In example 6, we're looking at a microphone, and it's on the sideline of a football field, and it's collecting all of the sound. And since it's collecting all of the sound, that sound should reflect back to the focus where the microphone is. So we want to know, where's the ideal place to place the microphone? And the answer should be on the focus of the paraboloid. So we're looking for the focus. Now, in order to find the focus, we need to find h, k, and p. But because this is something in 3 dimensions, we don't really have an axis for it. So we're going to set up an axis for it. Okay, so we have a reflector to catch the sound, to aim it toward the microphone, that is 3 feet across and 1 feet deep. We can put this anywhere we want in the plane. So why not put it with its vertex at 0, 0? So we chose to put the vertex at 0, 0. Now, because the location of the microphone is going to be relative to the disc or the paraboloid, it doesn't matter where you put it in the plane. If you said instead that you want the top of the dish to be the x-axis, you could do that, okay? The dish is 3 feet across and 1 foot deep. So this distance here is 1. This distance across is 3. Well, because of a parabola's symmetry, I know that if this is 3 feet across, this is the middle, so this is at negative 1.5, and this is at 1.5. So that gives us these points on the parabola of negative 1.5, comma 1, and 1.5, comma 1. If our vertex is at 0, 0, we know h is 0 and k is 0. So we have hk, we need p. How do we find that? Well, I also have an x and a y value. And it doesn't matter which point you use, you'll end up with the same value for p. So we can find this is an upward facing parabola, so the x is squared. So x minus h squared equals 4p times y minus k. X is 1.5, h is 0, squared equals 4p. So notice if we use the negative 1.5, because it's squared anyway, we'll get the same answer. Y is 1, comma k is 0. Oh, sorry. Minus k is 0. So we have 1.5 squared equals 4p divided by 4. P equals 1.5 squared over 4, which, put it into your calculator, you will find that it is 0.5625. Now this is 3 feet, 1 foot, so this is in feet. Now, if I have 0.5625 feet, I wouldn't describe it in feet. If it was exactly half a foot, I might describe it in feet. But really, if it's something like this, we would usually describe it in inches. And therefore, I can change from feet to inches by multiplying by 12. And I can find that this is 6.75 inches. So, if the focus is 6.75 inches away from the vertex, that means that the mic should be placed 6.75 inches above the base of the, what do they call it? Reflector. And that is why it doesn't matter where in your coordinate plane you draw your reflector, because the answer is going to be in respect to the reflector, not with coordinates from the coordinate plane. All right, at this point you should have everything you need in order to try the Math Excel, but if you have any questions, please feel free to email me, and we'll talk about it at the beginning of next class as well before the homework quiz.